Hello everyone, and welcome to today's webinar, where we'll be taking a look at ways to reduce heating and cooling costs in the commercial sector, including a look at zero spend options and a review of the Renewable Heat Incentive. My name is Vanessa Delgado, and I look after the supply chain portfolio on 2 Degrees. I'm delighted to welcome our presenter today, Dave Pearson of Star Refrigeration. Dave has a wealth of experience in this area across a wide range of sectors, and his presentation today will last for around 40 minutes. Which will leave us with 10 minutes for questions at the end. Now, before we actually begin with the presentation, I'd just like to remind everyone that you can submit questions throughout the webinar using the Q&A box on the bottom right-hand side of your screen. Just type in your question and then press send. We'll wait until the end before answering as many as we can. Now, if you have any technical issues during the presentation, please use the chat box on the right-hand side to send me a message, and I'll get back to you as soon as I can. So, without any further delay, I'm going to go ahead and hand it over to Dave, who'll get us started with today's presentation. Dave, are you there?
Yes, I'm here. Thank you. Thanks for the introduction. Welcome, everybody. This is a subject that's been close to my heart for several years now. I always feel the bad guy when you hear things like 15% of the UK's electricity is used for cooling. It's hard not to feel guilty as somebody representing a refrigeration contractor. I suppose the saving grace is we're always trying to do the minimum quantity of energy. So we've picked up some tips along the way, and I'll hopefully share these with you today. I'm not Harry Potter, though. I can't really do it for you. It really will come down to what you're prepared to get up and go and look at for yourself. So what to look for in efficient system design is the heading, or we might have said where to look for inefficient system design. It's fair to say that regardless of the quality of the system that's been put in, it's always possible to run it worse than intended. It's very rarely possible to run it better than intended. So, sad fact of life is it's probably not as good as it says in the tin. So go looking for areas where you can get it back to that base standard. So I did some lean management stuff a few years ago and was taken by this tag of muda or waste, which I thought was just a really over-the-top way of talking about some theory, some application, and some life. I'd intended to show a video here, which you're welcome to go and look at afterwards, but the video doesn't play quite so well across WebEx, so we'll not do that just now. But I always remember seeing this episode of Harry Enfield where the character turns from a 12-year-old into a 13-year-old, and that, I think, is a little bit how we all behave, where we start saying, oh, it's not my fault, it's not my problem. Well, if you're anywhere near the electricity bill in your facility, it really is your chance to be a hero. If you can be the one that goes and saves 20% off the energy bill, that's a massive amount. We're seeing clients who have an energy bill that's as high as the profit margin on their facility. Now, if you can take 30% off the cost of the energy bill, then quite clearly that's going to have a massive impact on the bottom line. So, sorry the clip didn't work, but can't be bothered is really the tagline. So, where to look for? Well, temperature lift is the first area. Where are you taking the heat from and where are you dumping it to? It's a very simple concept, but it's amazing how often it gets lost in probably the detail of what's going on, and frankly, the refrigeration industry has to hold its hands up to a certain extent and take some of the blame for this. We start using jargon like superheat and head pressure and other sorts of funny terminology, but frankly, we all need to get together in a language that we can understand. What I'm talking about here is what temperature are you doing your cooling at and what temperature are you throwing the heat away at. The closer they are together, the less electricity you'll have to use for your facility. So go and find out what those two numbers are. The temperature that you're throwing away at, the temperature you're getting your heat at, referred to as the evaporator temperature, should be no more than 3 or 4 degrees below the thing that you're cooling. So if you're cooling glycol from 12 degrees to 6 degrees, or water from 12 degrees to 6 degrees, you shouldn't be evaporating much more than about 3 degrees below that. And just to prove that we throw in some jargon, the refrigeration industry, we don't talk about degrees C temperature difference, we talk about Kelvin, and we don't even talk about degrees Kelvin, it's Kelvin. So that's us just trying to be really sneaky and trip you up. So my apologies on behalf of the industry. The operation of the evaporator, how well is it performing? Is it performing close to that theoretical design, or is it much further away? Condenser design, this is really where things start getting out of whack. It's quite hard to have an evaporator that's not performing reasonably well. It's very, very easy to have a condenser that's performing really pretty crap. The simple reason is, whether it's an air-cooled or a wet condenser, an evaporative condenser, you're basically sucking through a lot of air in this condenser, and that brings with it pollen seeds and dandelion seeds and all sorts of fluff and crisp bags and leaves and stuff that just chokes up. Go and look at it. If it looks dirty, it's not working right. It's effectively going out on a summer's day with a duffel coat on, and that's clearly not a good idea. So go and look at the condenser, but check the temperature at which the heat is being thrown away at. This is called in the plant either condensing pressure or it's called head pressure. So go and find out that number. And here's the other rule of thumb. That shouldn't really be much more than about 15 degrees above whatever the ambient condition is. Some plants, just by virtue of the nature, even on a very cold day, have to artificially keep this temperature much higher, and that's just a feature of their design. It can be improved, and we'll come on to that slightly later on. But go and check what the number is first of all. That's the first thing. Find out exactly what you have before thinking about what to do. And of course, the operation. How is the condenser being operated? And that gets into some really quite tricky stuff. Do you have air in your system? All sorts of other things that can be messing up the actual operation of the condenser. Quite a challenging one, this part load operation. There's been a big trend in the last few years for variable speed drives, and in some cases that's a good idea, but like most things in life, the same thing isn't always necessarily a good idea. So when should you use part load and when should you not use part load? When should you use variable speed? When should you not? And you really need to ask the questions about this. A cold store, for example, will be far more efficient if you run the compressors at full speed and full loading and switch them off for periods of time. Running most compressors at part speed generally reduces the efficiency. In some cases, not by a terribly great amount, but in other cases, it can make quite a significant difference. The thing to remember about variable speed drives is, if you're running at 100%, they will consume more electricity than if you don't have a variable speed drive. It's a piece of kit that has a loss attached to it. It's a couple of percent, but over the year, that's quite a lot. So sometimes it's better just to switch the stuff off and let the temperature rise maybe a degree and then switch it back on again. It's kind of hard to be precise as to what the best thing is because it's very dependent on what you're doing. But ask your service provider what's going on in the site. Get involved with it. And of course, there's the auxiliary power stuff. One of the worst examples, I'm trying to pick my words carefully here, one of the worst examples I saw was a factory that had a chiller, and for some reason the chiller wasn't required anymore, but the glycol pump that was feeding glycol from the main loop through the chiller was still running. It was something like a 50 kilowatt drive motor, and just because the classic huffy teenager just didn't bother anymore, that's somebody else's job to look after that. Then sadly, that pump was running when it could have been switched off. 50 kilowatts, 24/7. That's quite a chunk. Just quick calculation: 50 times 10 pence for electricity is £5 an hour times 8,000 hours a year. Because somebody couldn't be bothered switching that pump off, that was costing the site £40,000 a year. So, choice of refrigerant. This is slightly more, I wish I might have done it differently at some point in the past. At the same time, though, it's kind of glass half empty, half full. Maybe if you're sitting there with a chiller that doesn't owe you so much, and you're thinking, well, it's still working, so I won't bother thinking about it too much, maybe this is a brilliant opportunity to start taking major chunks off your energy spend. And we certainly, and other companies can do that for you. And we'll see some numbers here. So, choice of refrigerant. In the top area here, we have R404A, so a fairly classic HFC, and I'll say a little bit more about HFCs and where they seem to be heading in terms of legislation at the end of this slide. But just looking at the selections here, and I filled in this box in advance, so if we were evaporating at 0 degrees and condensing at, say, 30 degrees, then we'd get a coefficient of performance, the number of units of cooling over the number of units of electricity, of about 3.4. Now, if for some reason we could adjust the temperatures, we would make that better. Likewise, though, so if we could change from condensing at 30 degrees, so this is the condensing pressure I was talking about, by dropping that down by 10 degrees, we can get a 28% improvement in the performance of the plant. Now, clearly on a warm day, the condensing pressure is still going to be relatively high, but what about winter days or fairly cool days? We've got a fairly cool climate in this country. It doesn't get terribly warm all the time. What if we can get the head pressure, the condensing pressure down? 28% improvement just by helping the condenser, by making sure it's clean, maybe having the right sort of valves and the control philosophy for that. What if we changed refrigerant though and did that? We see a 49% improvement from 4.2 up to 6.27 just by changing the numbers and the gas. Now obviously you can't take an existing system, take one gas out and put a different gas of a completely different family type, but you've got to bear in mind that only 15% of the life cycle cost of refrigeration equipment is the capital cost. The vast bulk of it is 70%. So what that really tells you when you start thinking about the life cycle cost is it's never too early to replace kit that's costing you a lot of money in electricity when it shouldn't. What if you could reduce the running cost of your chiller by 50%? Would that not be worth doing today rather than 2 or 3 years down the line? The interesting thing about the financial market now that all these bankers aren't buying and selling bits of paper in Texas trailer trash parks, they're actually looking for something better to do with their money, and there's quite a few schemes about where effectively you can save as you use. So someone else will pay and own the asset, and you have the opportunity of getting brand new kit and getting the benefits of that. Reminds me a little bit of renting colour TVs in the 70s and 80s, but that's just me showing my age. So we see a big difference there. And if we start moving the evaporating condition as well, then we can see even bigger changes. So it's just huge the amount of benefit that you can make in plant just by making sure that you've got the right kit and it's set up correctly. So a little bit of a recap. Even the best designed system can be badly applied. Thinking of a particular example here, supposing we've got a chiller that's 1,000 kilowatts and we're doing 12/6 cooling, but in springtime we've got lower air conditioning requirements, so it's only running half loaded. The classic thing that somebody would want to do is fit an inverter onto the glycol pump, push less glycol around the system because the glycol pump consumes a lot of electricity. I always think it's a very simple rule of thumb: aim for the biggest motor and work there first. So if we don't follow that rule, we put an inverter on the glycol pump, we slow it down, and we might save 50% of a 15 kilowatt drive by buying a fairly expensive drive, variable speed drive. Now in some cases it's the right thing to do, in other cases though, as I'm about to show you, maybe just setting the system up differently is better. Supposing instead of feeding out a quantity of glycol at 6 degrees and it's coming back at 9 degrees, we said, well, actually, we'll feed out the same quantity of glycol, but we'll feed it out slightly warmer. I mean, it's only common sense, really. You see it with your boiler system. You can turn the temperature down of your boiler in springtime and still get the heating required for the building. So there's a really good rule of thumb. Every degree that you change the operating conditions of your plant, whether that's on the cold end or on the hot end, you make a 3% change in its performance. Now, if you widen that temperature difference by 1 degree, you make it 3% worse. If you narrow it, you make it 3% better. So raising the evaporating condition of this plant so that the glycol is going out at 9 degrees instead of 6 degrees will make a 9% difference in the energy consumption. Now, the motor on the chiller is likely to be far bigger than the motor for the glycol pump. So 9% of 125 is 11.25 kilowatt saving. Now, that doesn't look very much difference. The big difference here, though, is option A costs you a fair chunk of money. Option B costs you a bit of your time. So, as I was saying earlier as well, inverters cost more to run at full speed than running at fixed speed. So be very careful that they're properly deployed, or you could actually be making life worse. So here's the summary. Take a step back, consider the whole picture. Be rigorous in the application of efficiency principles and ruthless in the elimination of bad practices, really sloppy practices of leaving things running. Be prepared to pay if necessary, but lots of good practices and no-cost option. Now, we can't actually run this video, but there's going to be an email at the end of the session with the link to it. I don't imagine anybody's going to scribble down this YouTube link. But basically, it shows that plant that's being run well can be 50% better than plant that's run badly, and just across the whole board. And you see the numbers here. The condenser not being operated correctly makes a 25% difference. Having the refrigerant charge wrong or with contaminants is a 5% difference. Having, if you happen to have a cold store, having oil in the wrong part of the system, or having the coils frosted up, can make a 9% difference. So lots of different areas, and I strongly urge you to go and find this video. It's on YouTube as well, and check it out and see if there's any potential savings. They're all pretty much very low or no cost options on how to make your plant perform better. And as I said, it can make a 50% difference between a bad plant and a properly maintained plant. So going from the easy stuff to stuff that's a little bit harder, we did a project at Nestle. It's been the subject of a 2 Degrees webcast, including a great guy from Nestle, Ryan McNeil, where he gave us some of the philosophy behind it. What really struck me about this, and it was my takeaway from the entire experience, was there's no substitution for getting data and more data and more data. This guy had fantastic telemetry and some great assessment of what was happening with the data on his site. Sadly, too often we go and see a site and the best they've got is what the gas bill for the entire site is. That's completely hopeless in terms of trying to make the energy efficiency of the site better. You need to know where you're consuming the heat. If we take it to a simple domestic situation, you need to know which room of your house you are running the radiator in far too much, where it could be turned down a little bit. It's no good just knowing what the overall gas bill is. That's just going to depress you. It doesn't necessarily inspire you into being able to take any meaningful action. So Nestle had lots and lots of data. It was absolutely brilliant. They also had a fairly classic opportunity at the moment. I'm seeing a tightening of the R22 situation. If anybody's got any R22 still left in their site, by all means pop a question into the box and we can have a chat about it. But I get a bit embarrassed in this project. I promised that we wouldn't use too much extra electricity in order to recover heat from the plant. And I did all the numbers and showed there was a modest increase in electricity. What actually happened was that the chillers they had on site, which, you know, they were making a noise, the fans were spinning and they were delivering cooling to the process. So in a certain assessment they were working. In reality, they were so limited in their design and limited in the maintenance of them that they had an opportunity to replace them with something that was a design change better. So they went from an HFC or an HCFC, in this case R22, which is being phased out pretty soon. You can't even buy top-up gas at the end of 2015 or 2014, I think. And they took out the crappy old chillers and put in a new ammonia refrigeration system, and now get their hot water at 65 degrees effectively for free. What a fantastic situation. So we're recovering heat at 65 degrees at lower cost than then throwing away the heat at 40 odd degrees. And these next couple of slides give a little bit of detail, and there's a whole bag of detail at the end of the presentation that you can look at if you're more interested in this particular case. So where were they starting from? It really was pretty grim. It was the last Nestle site in Europe to be burning coal to make steam. We had a fantastic realization during the project that their boilers were something like 80% efficient. but the steam distribution system was something like 60% efficient. So they were actually only getting 50% of the chemical energy from the lump of coal into the process. So a great opportunity. And this is what it looks like now. There's 4 compressor packs using filter compressors. The ones that you see the lagging all the way up are the heat pump ones, and the others are the regular ones. They all look pretty much the same though. So you see the drive motor and the compressor. So it won the 2010 RAC Cooling Industry Awards. I always find it quite amusing when you win a cooling industry award for a heat pump, and we won a heat pump award for a cooling plant that we did once, but that's just quirks of life. So proven savings. This is really what it came down to. We were doing two different heating loops. One was a CIP loop, which is open loop, so heating water from 10 degrees to 60, and the other is a closed loop, which is used to keep the chocolate molten in the pipelines. And that, in total, was saving £700 a day, which is quite a significant saving. The interesting thing was, and they really were in a lucky position. The A had the data, that was their own good luck, and B, they had plant that needed to be replaced. It's always much easier to get sanctioned for something when you have a bit of kit that's pretty half-knackered anyway. And they had to make a greater investment, but if I understand the numbers correctly, they basically got their money back in the first year. There was a lot of process stuff done on the site as well in terms of glycol distribution systems. So I think the overall project cost was higher, but our part in this was about 300,000 more expensive, and the total project was saving 250,000 a year. The plant will last for 20 years, and ammonia is going absolutely nowhere in terms of being phased out. It's here to stay. So there's no risk in that as well. So a little bit closer look at what the theory of heat recovery is. This is the classic bit. You've got a chiller, and it's doing 600 kilowatts of cooling and absorbing 200 kilowatts of electricity. On the same site, and invariably this is true because very few people cool things down just for the hell of it, invariably you've got a boiler heating something up elsewhere in the site, and then you're having to cool it back down again. But the boiler will typically be about 85% efficient. So you're consuming 1125 kilowatts of heating energy, and you're doing 200 kilowatts of electrical energy and achieving 600 kilowatts of cooling energy. What if, instead of throwing that heat away, we could capture it? Now, we call it a neat pump, N standing for natural, and we're doing the same amount of cooling. In theory, we should be using more electricity, and we certainly are. It's only by comparison to the old chillers we're using less. If we ran this plant in cooling-only mode, it would consume less electricity, but we wouldn't get any heating. But the real Brucey bonus, as they say, is that not only do you have to spend more electricity, but you get all of that back, plus the cooling duty back as heat. So we're getting 900 kilowatts of heat available from our 600 kilowatts of cooling. And what does that mean for the numbers? Well, if we look at this graph, this is per hour. Instead of costing £59 an hour, which is for some electricity and some gas, it's costing about half of that. Now, big tension in large industry in the UK at the moment is the carbon reduction commitment. I understand that last year was the first year where the finance directors had to get the checkbook out and write a check for this scheme, and that's really bringing into focus people's requirement to get the carbon footprint down. Been to quite a few factories recently, and there's some really tremendous opportunities to not just reduce the carbon footprint, but to make big savings in the actual running cost. And that's why the scheme was set up, to encourage people to be more efficient. And maybe at some point in the future we can do another case study on a particular factory I'm thinking of. But basically they will be able to capture the waste heat from their chilling circuit and deliver it for washing processes in the factory. So in terms of carbon footprint, and of course the other opportunity you have, instead of burning gas or coal or fuel oil in a boiler, which is pretty much always going to have a carbon footprint, you could, if you chose to, electrify your heating. It sounds a bit of a grand way of saying it, but you could do your heating through a heat pump and decide to buy your electricity at zero carbon electricity and have an even bigger effect. So this scheme on the left here would be 325 kilos of CO2 per hour. And if we switch to grid electricity and heat pump combined heating and cooling, it would drop to 150, but it would actually drop to zero if we used zero carbon electricity. So it's very much thinking about the long-term value, and this is what I was hinting at earlier. The equipment is actually the smallest of the three parts for a large industrial facility. Maintenance over the 20-year life will be slightly higher than the capital cost, and the energy is the absolute largest amount. And this, I've not heard anybody that tells me it's going to go down. There's quite a bit of debate at the moment about energy costs and where it's going to go with new technologies like fracking and so on. But as you dig below the press, the broadsheet press, and start talking to some of the experts, what they're actually saying is we think we might be able to just about keep our gas price level in this country using fracking rather than having it escalating. So we're not going to see energy cost dropping any. So don't sit back waiting for a miracle. And that's what we're trying to do. We're trying to get the maintenance costs down, and we're trying to get the energy costs down of the system as well. So it really is about the lifespan. The other aspect is, depending what kit you put in, how long it's going to last. Is it 5 years? Is it 10 years? Realistically, that chunk of metal should be lasting 20 years. And this is what I was hinting at earlier about HFCs. European Union has just voted in the Environmental Committee that HFCs will be phased down to something about 15% of current levels by 2020. Now that's only just over 6.5 years away, and basically what that means is HFCs are if the law is passed through the Commission, HFCs are going to be phased down. So what I would take from that is use an HFC if you want to. You're not going to have to take plant out. They've never done that in the past with CFC or HCFC, but at some point in the future, non-natural refrigerant plant is likely to have to be swapped out for natural refrigerant. Why not, if you're planning new plant, just do natural refrigerants now, get the higher energy performance, get the opportunity for heat recovery, and put that whole problem area to bed and concentrate on making pies or cakes or sausages or whatever your business does, and take this off the agenda. Really, you shouldn't be having so much attention to what's going on in the refrigeration side of life. It should be very forgettable. So what are we doing with this? And a little bit of talk about the heat pumps. This is a project that we've done in Norway. It's a 15 megawatt district heating scheme at 90 degrees. It's a project for I think it's the Norwegian Army. We're basically heating the barracks by cooling down seawater. And we are doing a process in the south of France for Danone, which is a dairy. We're recovering heat. And of course Nestle as well. All of these are part of our competence of heating now. And it's really proving to be a fantastic opportunity. District heating is all over the press in the UK, largely driven at the moment by people intending to burn different types of fossil fuel. But I think the RHI is going to come in and do something better. Quick word on the RHI. Basically, at the moment, if you are adjacent to a river or a large reservoir or a pond, you could be doing your heating up to 90 degrees using heat pumps and earning a subsidy, which at the moment is roughly equivalent to gas. There is a rumour that it's going to be doubled, or in fact it's more than a rumour now. It's a stated intention of the government to double this. So putting it in broad perspective, and maybe you've got nothing to do with the food factory or cooling, but let's say you had an exhibition centre in a city. There's one in pretty much all of them, and it's next to the river, and most of our cities are next to rivers in this country, bar just a few. But instead of having a £150,000 gas bill, if you used large heat pumps, and I don't mean small domestic heat pumps, the efficiency on them is just not good enough, but to get up to the high temperatures, these larger buildings need water circulating at 65, 70 degrees, maybe even 80 degrees. But if you were to use a river-sourced heat pump, then you would be able to claim the RHI. Your heat pump would cost about $100,000 to run compared to $150,000. So a £50,000 saving, that's pretty good. It's about a third of the energy cost. There is, of course, the equipment to pay for, and that's typically about £400 per kilowatt for large industrial heat pumps. But by switching to that system and being a renewable heat incentive, the incentives for that scheme would be about $230,000 a year, so larger than the gas bill, and secured for the next 20 years. So my prediction is we're going to see a bit of a rush towards renewable heating done by large heat pumps. Anybody that's fortunate enough to have a large heating bill, I know you don't feel fortunate normally, but if you're fortunate enough to have a large heating bill and you're fortunate enough to be next to a large body of groundwater, being a lake, a reservoir, or a river, then you can do natural heating. You can do boreholes as well. The centre of London sits atop a water table which is around about 14 degrees. We've done a couple of heat pump projects in London already, one for Hyde Park. It's maybe not the most attractive part of the £125 million penthouse part, but it's a heat pump, and it takes heat from the reservoir underneath the city, the water table. We've done a couple of units for Tate Gallery as well, Tate Modern. So, getting close to the end, why a heat pump and why use waste heat? Well, there's lots of reasons. The first one is the carbon footprint we talked about. The second one is the financial. The third is your corporate and social responsibility statement. Most of the large businesses now have this. If you want to make major dents in your energy, you're going to have to do something other than switching off lights and remembering to put your PC switched off at night. We're going to have to really address energy. Absolutely staggering statistic, and every time I remember it, it just blows me away. Over 50% of the UK's energy is for heating. Excluding transport, it's about 70% of our heating. Our energy consumption in this country is for heating. So we have the opportunity to deliver this heat at zero carbon, and that's why I think we're going to see large heat pump facilities popping up, and that's why it fits. Long-term security, it's your chance to get away from HCFCs and HFCs by using a natural refrigerant large heat pump. Here's an interesting quote from Professor David Mackay, the government's chief scientific advisor, and he said, "Setting fire to chemicals like gas should be made a thermodynamic crime. If people want heat, they should be forced to get it from heat pumps. That would be a sensible piece of legislation." So, what exactly does a heat pump do? Well, we've spoken about it a lot today, but basically, it cools down one part of the system and heats up another. A large heat pump could perhaps have a COP of 4 or 5, so you're basically getting 5 units of heat out for only putting 1 unit of electricity in. So, you can understand why he thinks it's a thermodynamic crime to set fire to something at 1300 degrees, something that could be used for far harder, far more valuable tasks like making steam to run some of our industries. Why are we burning gas just to heat our homes to 21 degrees and our sanitary hot water to 50 degrees? It's completely nuts. That's his point of view, and I share it. So really, it's proven, and what makes a good opportunity? Well, it comes down to design. It comes down to having a good heat source. You need a user for the heat. There's a couple of common pitfalls. Let's quickly zip through these. We're a wee bit short of time. Basically, what we're having to do is get the system design temperature as high as possible. This is for a heat pump as well. So if you're doing useful cooling and heating, try and get the cooling fluid down. Here's an interesting graph. So it's COP in different colours and evaporating temperature versus condensing temperature. So if I pick a typical situation, Nestle, for example, was 0 to 60, then we'll be down here, the bottom left-hand corner, we should be thinking a COP of 3, 3.5, something like that. But of course, we're doing useful cooling as well as heating, so it's effectively double that. So it's half the cost of burning fossil fuels. Sometimes we see ourselves way up here. We want to take heat from -10 and heat it all the way up to 80. You'll get a COP of 2-ish for that. It's just really not good enough. However, sometimes we can be doing things like data centres. We could be cooling our data centres at 20 degrees and delivering the heat at 60 degrees. We could have a COP of 5 just for the heating part of it. So getting the temperatures right is correct. And generally, we want to move in the direction of the arrow to move the COP up higher. Sources of heat: air, factories, data centres, reservoirs, large industry. They go into the heat pump. We put some power in and we can get hot water for heating, hot water tank, central heating, desalination and dehydration. The same kit that we did for Norway we've been looking at using that in the Middle East. We can do district cooling, but recover all the waste heat and use that for desalination. If the UK's estimate is 15% of their electricity is for cooling, in the Middle East it's 60% of their electricity is used for cooling, and all that ends up as waste heat and thrown away, plus the stuff they've been cooling down, the buildings. They're throwing away a quantity of energy in the Middle East which is about 2.4 times the total electrical output of the region. Now, what does that mean in something more tangible? It's the same energy as is contained within the annual barrel output of Q8. It's being thrown away as waste heat from cooling systems in the Middle East. They also have a major water shortage. Maybe, just maybe, they'll join the two together. So, common pitfalls. A heat pump is not a boiler. You can't use a heat pump to send steam around your building at 130 degrees. So, you need to think about the boiler. Also, think if you are replacing kit, this is your opportunity. Don't just put a regular chiller in. This happens to be our ammonia chiller called Asian chiller, but go for something with heat recovery in. And it looks a little bit like that. So, final step, billing data. Get your billing data. First of all, know how large the bill is. That's the size of the prize. Think about where energy is consumed. This does mean a bit of hard work. You've got to get in amongst it and start metering on your site. Metering hot water services is not easy, but if you don't do it, you don't know where you're actually consuming the heat. It makes no difference knowing how much your boiler is doing if you don't know where you're consuming the heat and at what temperature. In Nestle's case, they were consuming the heat at 50 degrees all around the factory. Until they measured that, they didn't know. And secondly, challenge the experts. Don't sit back and listen to these guys that come and tell you they know everything about it. Go and swat up on it. Go on YouTube. Go on Google. Find out what's going on. Phone me. That's fine. Send me an email and we can chat through it. And then go back and challenge the guys as to how they're going to improve your carbon footprint. So that's the first page of the Nestle case study at the very end. So that's the end of this part of the presentation. I see there's some questions have popped up. Lucinda, is it okay to answer these just now?
Yeah, you can go ahead and answer this one right now if you like.
Okay, so the question from Kes Tobias is, of the reasons you gave for installation, finance, CO2 emissions, commitments, etc., right now, which are you finding is the hardest barrier for the companies you've been working for? Without a shadow of a doubt, it's finance. If I said to you, I've got a project, and it's a 3-year break even, but you don't need to do it, effectively what I'm saying to you is I'm going to make you poorer for 3 years. That is not a good proposition to be taking to any business at the moment. Times are tough. Everybody's short of cash. My proposition would be twofold. Firstly, do you aspire to be in business in 5 years? If you do, and I'm not being flippant, if you aspire to be in business in 5 years, then you need to start addressing your energy consumption now. There's no point waking up in 3 years and saying, damn, I wish my energy bill was less because I'm getting a complete doing from my competitors, my customers are squeezing me. So finance is the hardest bit. The second bit to say to that is there are companies out there that want to take that burden from you. Of course they want to make money from it, but providing you a reasonably good opportunity, effectively what you have to enter into is, for example, a 7-year energy purchase contract. But if you enter into an energy purchase contract, they will agree to sell you heat at a lower cost than what you're paying now. So basically, you can be better off in month 1 of deployment, not month 37. You won't be as well off because somebody's making a cut on it, but that's your choice. Raise the money yourself and buy it or lease it. So I hope that answers the question. Are there any more questions here?
No, you can go ahead and keep going forward at the moment.
Okay, thanks for your reply there. So, actually, sorry, it was four parts of the same question answered in one. I'd say, just to put a slightly different slant on the question, CO2 emissions is the one that's actually maybe driving things. That's what's put this whole area on the agenda of the finance guys. We never get terribly far when we're talking about engineering for something that you don't need to do in a business. we tend to get much further if it's a financial proposition with the finance director. So wave the numbers in front of the finance director and tell him that if he doesn't agree to do this, he's costing his business a 20% saving on his energy bill, maybe even more than that. So I think that's just about a wrap for today, unless there's any last-minute questions. But I hope that's been useful. Find me on LinkedIn or drop me a mail. And good luck. Thank you.
All right, thanks very much, Dave. I actually did have a question that came in from much earlier, so if I could ask that one. So the question is, what are the implications of changing refrigerants with an existing system? What questions should you ask a potential supplier? Well,
there's broadly two families of refrigerants. There's HFCs or HCFCs, all pretty much the same thing, sometimes called freons, certainly synthetic refrigerants, and then there's natural refrigerants. It's, I would say, almost impossible to go from one to the other with the same kit. Ammonia doesn't mix well with copper, which tends to be the material of choice in HFC installations. So if you're looking to change from HFCs to ammonia, I'm sorry, pretty much tough luck. There are some other refrigerants that are popping up that are effectively, can sometimes be a drop-in for R22, but basically they are still of the same family. They might, for example, from R22, the ICN range of refrigerants are lower ozone depleting, and that gets you out of one challenge. So it's possible to do that. The implication, and probably what's driving this question, is how much effort should you go in terms of recommissioning the entire system? My answer is as much as you can possibly afford. When you change from one refrigerant to another, the oil types maybe need to change, and you maybe need to think about the seals, and that's a big part. There's absolutely no point putting new expensive refrigerant into a leaky system. Get it leak tight. So really spend the money getting it recommissioned back up to best possible standard, and then put the new refrigerant. Otherwise, it's just going to piss out all over the place.
All right, thanks very much, Dave, for that. So if we don't have any more questions for the time being, I think we've also gone ahead and reached time. So I'm going to go ahead and close up for the day. So I'd like to thank you, Dave, for your time today and for the presentation. It's been great, and we'll be able to post it up on the site for those who can attend today. I'd like to thank everyone else for joining our webinar today, for participating. So a recording of the webinar and the presentation slides will be archived on the 2 Degrees platform. I hope you found today interesting and useful, and you'll be able to join us for future webinars in the coming weeks. Thanks for joining, and bye for today.
Thank you.